Hello and welcome back to Mechanical Systems Design. In this video, we'll talk about Project 4. And hopefully we saw here again that the most effective processes were ones that blended together sketching, back-of-the-envelope analysis, finite element analysis, and other CAD tools, prototyping with low fidelity and functional prototypes, going back and forth between these processes iteratively in a way that's optimized to learn about the design domain and about your design, and trying to avoid getting bogged down in, say, too many details of a particular analysis, or pushing all the way through to a fully functional prototype before we've really thought about the simple model implications. As with Project 2, I think a really good way of doing this is just to walk through my own process for designing an example robot to complete the task and talking about some of the decisions as we go. This isn't the best design, it's just an example and gives us a chance to jump off and talk about the process. So we started with this very vague, wide open space for design. We have this door and we want a robot that is going to climb up its edge. So really no guidance on what the thing should look like. And we know that we want to pull the heaviest payload up possible. So as with projects 2 and 1, I found it really helpful to start here with a potato free body diagram of the problem. And so here we're just trying to see what the task can tell us about what our design should look like. And walk through this and see where it goes. So here's the edge of the door. So here we're looking at the door on edgewise. And this is sort of an imaginary robot with no features. And I know that I want this downwards force from the payload, that I want that to be big. Well, the rules are that we can't touch any surfaces that aren't vertical. So that means we're going to need some kind of friction force on those vertical surfaces on the edges of the door to counteract this downwards force from the payload. And since it's coming from friction, that means we're going to need big normal force. These are forces of the door onto our potato robot here. So we're going to need some big outward forces to provide a normal force that allows for friction to develop. Unless we were using some, gecko adhesive or another cool product that wasn't available to us for this project. Well, so this is one way to do that. We've got the force sort of centered on the door. We've got these vertical forces distributed evenly between the two faces of the door and some normal forces to get that. But the problem with this is the implication for the structure of the rest of the robot. So if we think about what kind of mechanism would be needed to create that force, here's my really jank spring here. You might need, say, a wheel on each side with some kind of spring or other thing that's pulling them together to create that normal force. And maybe you need some sort of a linkage or something like that, if we sort of move from potato to something more specific, to constrain those wheels so that they'd be right to the side of each other and so that the spring kind of pulls them in. And there are other ways you could imagine do this, but they all involve some kind of hinge that allows for those two wheels to be pulled closer to each other without any resistance from the structure of the robot itself. And that hinge here would add some complexity to our design. So if you find yourself having done a free body diagram that implies a relatively complex system, sometimes it's worth going back and reconsidering the assumptions that you made in that initial free body diagram. So looking at this one, we can sort of think about what are the big basic assumptions that we've made here. And one of them is that it would be good to have this payload force centered on the door. Well, what if we break that assumption, we violate that assumption? What happens? Well, the force balance in the vertical direction would still work out the same, and in the horizontal direction. But we could probably see pretty quickly that our moment balance is going to fail. If we pick, say, this point in the middle, we're going to, all the blue forces are going to sum to 0 moment, but this payload force is going to make the thing want to rotate counterclockwise. So maybe we can reconsider some of our other assumptions. How would we get moment balance if we put that payload force off to the side? Well, if we shift these reaction points vertically, then we would be able to get moment balance and achieve equilibrium. And further, let's throw one more assumption in there just for fun. Let's say we've kind of assumed that both of those points are going to be driven, but they don't necessarily need to be driven. Maybe we could just have one of those points be the drive point. And now let's think about the structure that is implied by this free body diagram compared to the first one. If we get rid of our potato and try to move to something more realistic looking, you can see in this case we could have a single structure that with no hinges or flexures, anything like that, and get the reaction forces that we want. And furthermore, by having one drive point, we wouldn't need complicated transmission to connect, say, this wheel down to this wheel, so that can make our transmission and connections to the motor simpler. So this is the direction that I went in designing this. I know some teams chose alternate paths that also worked out well. But this was my thinking, to try to keep a simple structure and avoid a complex transmission. Now, one thing to notice if we move from both wheels being driven to one wheel being driven is that we still need that vertical component of force to be equal to the payload. Now it's not distributed across 2 contacts, it's at just 1 contact. And so we need that friction force there to be twice as big. And therefore we need the normal force to be twice as big at each place. So there is a trade-off in that we need these bigger loads on our system, which could mean we need bigger structures. And as we sort of think about what exactly those forces will be, it becomes helpful to think about the key parameters in our geometry from this side view. And as usual, moment balance is really critical in understanding which lengths matter the most. If we do a moment balance about this point, we'll see that this reaction force from this passive wheel goes through that point, doesn't contribute. This vertical force due to friction on the drive wheel goes to that point, doesn't contribute. And we're left with just this normal force from this top driving point and the payload force. And if we do our moment balance, we'll find that we need this length divided by that length to be less than or equal to the coefficient of friction. The normal force and the payload force, which are not related, that the payload force will drop out. And noting that our friction constraint is an inequality, not an equality, but that the friction force is less than or equal to the normal force times the coefficient of friction if we have static friction, not sliding, not dynamic friction. And we'll get this. So it's going to be super important that we have the vertical offset of the wheels to be the right distance compared to the horizontal offset of the payload. And in fact, if we kind of reflect the change we've made by having this as it's, maybe we need that to be a little bit bigger so that we get more of a ratio that seems like the coefficient of friction that we would get for rubber on wood. And the way we might get that is by looking it up online, or maybe running some little quick empirical tests like the sliding board test that we talked about on top of it. Now, this free body diagram has other implications. If we look at it very carefully, you'll notice that we have 3 forces. Yes, there's 2 components of this force from the drive wheel, but there's just going to be 1 force vector at that point of the door onto our robot. And so we have a 3-force member. And as we learned earlier in our discussions of free body diagrams, 3-force member is a special case where we know that there must be one place where all three forces intersect. The lines of action all intersect. And in this case, we know that our passive wheel, to a reasonable approximation, will have a reaction force that's normal to the surface that goes out this way. And we know that the payload force will be up and straight up and down. And so this must be the intersection point. And therefore, the reaction force up here is going to need to go to that point as well. And that's going to allow us to adjust our sketch of the structure of the robot to make it even better. So if we say we want to avoid bending moments and put things in axial tension or compression, then we would want an element that mostly goes along this line between the rope attachment point and the drive contact point, and a separate element that mostly goes straight towards the passive wheel. And then maybe we'd have a little something to connect the two that would help prevent buckling in this element. So just by looking at the free body diagram from the door on its edge, we're able to get some pretty good ideas about what the structure of our robot could look like in that direction. All right, now let's look at the front view of the door. So here we've got some of those forces, the normal forces that disappear. This is that friction force in the vertical direction. This is the payload force in the vertical direction as well. And this is a pretty simple free body diagram. You can imagine our potato design here, and we can achieve static equilibrium as long as these forces are collinear in this plane. So simple, straightforward, no problems. But there are some interesting implications of this free body diagram. For example, let's say that the heading of a robot as it's going up the door gets adjusted a little bit. Maybe there's a little bump, maybe there's some asymmetry in the wheel shape, something like that. And it causes it to rotate a little bit so it's headed more into the door. What's going to happen? Well, we can see now that our free body diagram is no longer in static equilibrium. These two forces are offset side to side, and so they're going to have a small moment that tends to cause this thing to rotate clockwise. And that's good in this case because we want it to rotate clockwise so that it's headed more straight up the door. And so it would restore the desired heading of the robot. Excellent. Now, what if we flipped that and we had it so that the payload force was higher than the driving force in our robot? Well, that would not be as good. If we get a little bit of a nudge in heading, a disturbance, it could be even tiny, infinitesimally small disturbance in the heading of a robot. Well, now this moment caused by those two forces is causing it to rotate counterclockwise, which tends to increase the amount of rotation, which further increases that moment. And so we have this unstable heading problem. So this is sort of like a negative trail in a bike or a caster wheel. We want a little bit of rotation in the system to automatically restore it to the desired direction. So that's something to keep in mind as we think about where the wheel should be in the vertical direction relative to the, say, rope attachment point. And in our initial sketch, everything was okay. How about from the top view? If we look at this thing from above and make now these are the normal force arrows. We're looking endwise on the rope or the payload force. Let's think about what we can learn about our system from that view. Well, this free body diagram is in static equilibrium as long as those forces are collinear. Everything is costatic. Maybe we get some wheels there. Maybe those wheels are going to be connected by some structure. Well, now we can start to see some things that we care about for our structure. If we take a cut right here, then do a free body diagram of our cut component. This is my, again, very quick up sketch. You'll see that, all right, we're going to need this force. This is that normal force due to contact with the door. There's going to be an equal opposite force over here, but they're offset. And that means that those forces will make this want to rotate clockwise. And we'll need an internal, we'll need a moment at that cut surface, and that's through the interactions between this portion of the component and this portion of the component down here. So really, this moment and this force are going to represent a pressure distribution. We have more tension on this side and either some compression on this side or just less tension on the outside edge of that element. Now, as we saw in many cases this quarter, we know that bending moments are bad for mass efficiency because they result in this uneven distribution of stress, and you need maybe a complicated structure to maintain a reasonable amount of mass efficiency despite the moment, or you end up with a lot of material that is not really carrying its own weight. So we want to keep those bending moments as small as possible. And this free body diagram tells us, therefore, that we should try to put those normal forces as close to the edge of the door as possible. Now, of course, on the other hand, if we have some infinitesimal nudge, in this case, we're going to slip off the door and fall, and that's catastrophic. So we need some factor of safety. And we'll probably want to offset these from the edge of the door by as little as we think we can get away with without slipping off the door during that lift. And there's one more thing that's worth thinking about here, which is, we've drawn this free body diagram assuming that everything is perfectly aligned and the robot is going straight up. But what if there is a little bit of a force effectively to the side in this free body diagram? Maybe instead of looking at the robot exactly from the top, we look at it from a slight angle. Maybe the robot heading has shifted a little bit so that that gravitational force on the payload encodes a small side-to-side force. Well, what we should see quickly is that we don't have static equilibrium. This is going to want to spin counterclockwise as I've drawn it. And if we can easily have force in the opposite direction and want to spin clockwise. And these forces being not offset at all side to side, in order for us to achieve static equilibrium just from these forces, we would need them to become infinite, so that an infinitesimally small side-to-side offset would lead to a finite moment to overcome this moment. And that's bad, right? That's going to put big forces on our structure. So this gives us a reason to set our wheel width. The wider these wheels are, the more the center pressure for their interaction with the door can move side to side to create a reaction moment to resist moments caused by, for example, the heading shifting a little and the payload causing a moment in this plane when looking at the robot from directly above it in its reference. And so the wider those wheels are, or if we had maybe multiple passive wheels or multiple driven wheels that are all offset, then the larger a change in heading we could handle without getting this, having the center pressure get to the edge of that contact patch, and then we have this, big force multiplier, and we start to barn door off of the door, where instead of kind of being lined up, it goes. So just by looking at the free body diagrams of this thing from 3 different views, we can start to get a sense of some of the potential issues that we might run into and the overall structure of our robot that is going to allow us to overcome those problems with a relatively simple design. Now we can start to get a little more quantitative. And one of the big questions that is going to influence our choices here is approximately how big is this payload anyhow? I'm talking about 10 grams or 10 kilograms or 10,000 kilograms. Well, a good way to get at that is by thinking about these other aspects of the task. Like we have to use this motor and we have a certain amount of time to climb up. So one way to try to understand how big that payload is going to be to think about how much work is implied by a certain payload and how much work can our motor do in the amount of time we have available. So if we start at that end and work back, we'll eventually get to something that we can try to answer, which is how much work comes from the motor. So remember that the payload weight, so the mass of the payload times gravity, times the change in height, that's the amount of work that we need to do on the payload. during this period of time. If we divide by the time, we'll get the rate of work, the power that we have to apply to the payload. And we know that the work out of our robot will equal the work in from the motor times the efficiency of the transmission. And we could guess at the overall efficiency just to get it back to the envelope, right? This might be wrong by, a factor of 2 or 5 or something, but it might be order of magnitude reasonable, let's say 30%, based on our experience characterizing our gearbox in Project 3 and, our theoretical understanding of the efficiency of custom gears from our topic reading subject. So then the question really is, how much work can we get out of the motor? We want to get as much work as possible in the 3 minutes available. Well, one way to do this, and we saw this in Project 3, is to just try to get the max power at the maximum voltage. So we saw it when we learned about our motor models that maximum power is approximately equal to 1 over the coil resistance times the applied voltage squared. And this tells us that we want our applied voltage to be as high as possible to get the most power out of the motor. And once we've selected that applied voltage, we can go through and figure out what's the stall torque and the maximum, the torque that corresponds to that maximum power for that voltage is about 1/2 stall. Now, the problem is that if we go through this, as we saw in our motor operating point selection flowchart, we need to check to make sure that we won't overheat our motor. And in this case, if we pick 6 volts and we pick the maximum power operating point at that voltage, we're going to have current that will overheat our motor before the 3 minutes is up. So we need to go back and try something different. And the first thing to do is, well, we've already done this in our check, but we can figure out what is the maximum sustainable current. And as we talked about in topic reading, there are 2 approximations we can use. One is to say, what's the maximum current that we could sustain indefinitely if we just ran test after test after test? And that would be this is the steady state tolerable current. This would result in the motor's temperature being the maximum allowable motor temperature at steady state. Or we could try something where we say, we're going to assume that we start at room temperature and we run for just the amount of time available, 180 seconds in this case. And we have a reasonable model of the motor time constant, thermal time constant. And then we can estimate what the allowable current for that period of time would be, where our temperature would still be increasing at the end of the 3 minutes, but we turn it off before it overheats. We might add a factor of safety to that. So this helps us to set our motor current. And remember that the current is proportional to the torque. And under some conditions, as the current increases, the power is going to increase also. So we probably want to be operating right at that current limit. But what voltage do we want to apply? Well, here we want to, again, apply the highest voltage that we can. So just as we know that more current means more electromechanical torque, more voltage means more speed for our motor. So if we fix our current and slowly increase the applied voltage, the mechanical power out of the motor is just going to increase linearly because the motor speed is just going to increase linearly. Remember that the voltage balance gave us that the applied voltage equals IR plus theta dot times the motor constant, theta dot K. And so if the I term is fixed, then that's not changing, right? And we're just going to get something that's linear in the applied voltage for the speed. And the mechanical power is the torque times the speed. So it turns out to, it might be a little confusing when you first start thinking about it, but if you look at the equations, you'll see quickly, this is just a linear relationship. For a given sustainable torque, you just want to maximize the voltage that you can apply. And so just as we would have thought from our maximum power strategy a couple slides ago, here again, best to apply the highest voltage we can get away with. So this means that really you'd like to ramp up that voltage as much as you can, still getting away with it, as long as you're not accidentally using that voltage to drive too much current through your motor, which could lead to overheating. So if you have good current control, then more voltage is just always better. And eventually, the reason that we wouldn't pick some infinitely high voltages, that as we ramp it up, we run into some other problems. With these brushed DC motors that we're using in this project, eventually we're going to start to damage the brushes. That starts to happen pretty quickly. As in, not too many cycles, around 12 volts with these motors. At higher voltages, we would have problems with our power supply. Eventually, in hundreds of volts, we'd start to maybe break down the insulation of our motors, or break down the transistors in our electric commutation for, say, a brushless DC motor. But for whatever system we have, within the practical constraints, we probably want to operate it at as high a voltage as we can. So what does that mean for our payload? Well, if we just plug in some numbers for these motors, for the thermal and electrical coefficients for these motors, we're going to find that for 3 minutes, we should be able to handle about 2.6 amps. And if we plug that into our other equations and push things through, assuming that we get the gear ratio that we need and use our guess for efficiency, that gives us something like a 25 kilogram payload that we can lift, which is enormous. And it has profound implications for our design. And that was calculated only using the motor model and like a one parameter estimate of our transmission. So you actually don't need to go through all the nitty gritty to have a pretty good sense of the magnitude of the load that your robot will experience. So looking back over this back of the envelope analysis, as always, it's critical to a good design. We made our biggest, most important decisions, like the structure of our robot, and set our expectations for how it's going to be loaded, what the magnitudes of the loads will be, what our gear ratio should be, all those things from back to envelope analysis. And as always, I've walked through it kind of linearly here, but it's really an iterative process where popping back and forth between sketches and back to envelope analysis and some MATLAB calculations, and then back to Botia and maybe some SolidWorks, and this isn't going to be convenient. Let's sketch out some other ideas, maybe a prototype, and you see something's different than you expected, as I did in this case, and you go back and, yes, I made a little mistake in my back analysis. And just to emphasize all that, I'm going to provide my actual notes for working through this project as a document on Canvas that you can get to. All right, so the next set of processes we use here were detailed design processes in SolidWorks or CAD of some kind. And so here you can see this overall shape looks a lot like what we sketched out. We've got this 3/4 member where there's this tensile element that's lined up with the contact point. We have this compressive element that's lined up with that contact point, and a little link to reduce the likelihood of buckling in that element. Here we have a huge, an enormous gear, so we can get nearly 10-to-1 gear ratio between our motor and the drive wheel, and the drive wheel is down here. And looking at from the side here, we've got this is a little sliding joint so that we can adjust the alignment of the payload versus the driving wheel, because we're worried about that heading instability being an issue, or being able to steer things. And so I thought being able to adjust that would be helpful. And so this is a slot that allows it to be moved in and out. The motor is just screwed right to this element here. So, and the holes are slightly oversized so we can get it adjusted right and then tighten it so that the gears will mesh properly. You can see that all of our rotating members have simple support. So here is one bearing for the main drive gear and drive wheel, and over here is the other bearing. So on either side of the entire thing. Same thing with the gear that attaches to the motor shaft. So we have the motor here is connecting it, and then there's that bushing built into the output stage of the gearbox that provides one of the bearing surfaces, and then on the other side we have a ball bearing there. So that element is in simple support. Also, we avoid having big force multipliers that cause high friction that would dissipate a ton of energy otherwise. And same thing for our passive wheel down here, simple support. This passive wheel has a pretty big radius, and that was chosen in part to manage the sizes of these two chassis elements, and in part to have low bearing friction, because you've got a big ratio of the radius of the wheel to the shaft radius, and to limit the effect of little bumps and imperfections in the surface of the door. The door that I was going to go up had a little bit of warble to the paint, and you could adjust that if you say we're going to be using a really, say, compliant material with the passive wheel, then the coefficient for the rolling resistance might be higher. It might be better to have a small radius. And you can see here we have several different holes, and that was based on the idea that the center hole is the one that I expected to use for the loading rope. That's along these lines of action of the expected forces. But I thought, oh, maybe my coefficient of friction estimate will be slightly off. It'd be nice to have some adjustability. So put those holes in. As we'll see, it wasn't quite enough. And here's a view from the top view. And you can see here we've got a pretty big margin here for heading without slipping off the door. And here's that main element that's going to experience bending. It will have a uniform bending moment all up and down this section, so it's uniform in its shape there. And here's an example. We can define an element analysis on all the components. Here's an example of that especially critical element there. And you can see, as we expected, we've got really high tension on the innermost surface there, and then sort of bending pattern. There's still some compression on the other side. And for this cross section, I roughed it in using back of the envelope analysis to get some of the parameters, and then iterated in finite element analysis to get some of these details, like the thickness of this bypass here, right? This introduces some interesting stress concentrations because you need the drive shaft to be able to get through here, and you need that drive shaft to have a pretty big radius to avoid failure due to torsion and shear, given the layer alignment from the print job. Now there is one point here where we've got a stress concentration that exceeding our factor of safety. I was counting on ductility to help there. Otherwise, we have to make everything a lot bigger, and it was already a pretty long print time. And this is already specified for 50 kilograms payload. Okay, so we went through this detailed design phase, but before we printed these components with like 1 day or 1.5 day prints, pretty big and thick, I wanted to make sure that things looked okay in the geometry. And so I just made a really simplified version of that clamping part. And it looked pretty good. Coefficient of friction seems to be at least what I had estimated. And I did notice, though, one little error in my free body diagram. I had aligned things not with the actual contact point, but with the center of this circle for this fake wheel on this component. And you can sort of see this is bent a little bit. It's hard to see in the picture, but it has just a very slight curvature to it, which was a sign that there was that mistake, and I went back and fixed it in the complete complexity design. Another thing that happened here that I didn't pay enough attention to at the time, but I wish I had, is that I when I set this on the door, it hung beautifully. And then as I was looking at it and taking pictures, all of a sudden, it just started sliding down. And that is behavior that is not described by a Coulomb friction model. And in fact, I haven't taken the time to go and read the tribology journals to try to get a proper description of this phenomenon. But in fact, it seems pretty clear that, and we'll see in some of the tests, and I'm sure you experienced this as well, the rubber behavior was not very consistent with Coulomb friction. And that was resulting in slipping in some cases where you hadn't slipped under the exact same required friction force and Miller force. We'll come back to that. Then we printed the full complexity design, and here's just an example of one of the components being set up. And of course, getting the slicing just right is important in getting your functional prototype to work well. Here we have a gear for a custom gear, and you can see it's full density on this outer edge. So we have pretty stiff surface to hold those teeth so they don't bend too much, which can cause them to grind or have higher friction. And here's like a support surface. We've got these fins so this thing has stiffness in this sort of outer plane movement. And then there's a central sheath there that provides the torsional stiffness. And that little tiny hole in the middle is where the support shaft is pressed. Okay, so then we started to run tests, and here you can see a few issues right away starting to manifest. So the reason we have to stop this test is because the heading is changing, and it's about to slip off of the door. And that was a consistent issue. And the solution there was to just adjust that slot joint over and over again, and try different initial headings until we found a combination of the initial heading and the slot depth where it climbed pretty consistently at least for the 0.8 meters. Another issue that you can see here is as it rotates, or as heading changes, the payload force starts to have a horizontal component like we were talking about, and it starts to make this robot want to twist off. And you can see here, there's just a little popsicle stick hot glued on there as really a safety mechanism, emergency mechanism, so that when it starts to rotate, that contacts the door and keeps it from just falling off. And so after playing with making these adjustments, and you can also see that the lever arm is extended here with popsicle sticks with this sort of janky I-beam or L-beam here, because as the wheel started to rotate, the effective coefficient of friction was much, much lower than when we hung the system on the door, and needed to increase that lever arm of the payload so that this length divided by that length was less than or equal to the apparent coefficient of friction. So after about 20 trials fiddling with it, finally got things set up pretty well with a good initial heading and a long enough lever arm and the right sort of offset of the wheels with that slot, that we're able to consistently make climbs with first 0.5 kilogram, then 1 kilogram, then 2.2 kilograms. And as the amount of weight increased, the apparent coefficient of friction of the rubber decreased. And so that lever arm got longer and longer. And so I've jumped forward a little bit here because it's kind of a boring video. It just very slowly climbs up. It took about 2 minutes. We're not operating anywhere near the current limit for overheating the motor. And so, the motor could have lifted quite a bit more mass than this, about maybe 10 times the mass. But the failure mode that we ran into was that as we tried to increase it, that nonlinearity and the apparent friction coefficient caused it to slip and slip, and had to make that lever bigger and bigger, and eventually couldn't climb the wall. This was with 4.5 kilograms, and during that fall there, the wheel, the big gear smacked the ground and sent a shock into the little gear, and the little gear broke. So if I were to try to do this better, to make it pull up a heavier load, I would redesign the system to have a smaller vertical separation between the wheels, so I could do a little bit better leverage that way instead of making the payload lever longer. And I would have tried more permutations on the contact between the drive wheel and the wall. So perhaps a thicker rubber, different kind of rubber, or maybe even no rubber, and we might get a more linear relationship between the normal force and the static slipping force. And another little tweak that I would have made is to give the payload rope a little bit more trail. So as that offset, the vertical offset of the wheels got smaller, I want to attach the payload rope below the lower wheel so that it would have this restoring moment as the heading changed, and maybe a separate adjustment for that rope attachment point. So that was my design. There were lots and lots of ways to do this project, and we saw some other great designs. I hope you'll go and watch the videos of your teammates, your classmates, robots climbing their respective doors. And I have to say, I was really impressed. This was a super challenging project, and we did quite well overall.
I have to say, though, that this project was pretty intense, and at times even a little surreal, almost dreamlike. Wait a second. Well, I hope that at least the design processes and techniques that we've been discussing are now deeply embedded in your psyche, where they'll help you to do better design work out in the real world.